Okay. Okay. So Fourier analysis, right? Fourier analysis on finite abelian groups. And so we're sort of asking, how do we generalize stuff that we had before? Right? How do we generalize the stuff we had before to this case? Are we able to generalize it to this case of finite abelian groups? What do we need? What do we need? So what do we need? That's sort of what you want to keep in mind. Right? And so remember we generalized one particular notion. The exponential functions that we used to reconstruct our old functions, right? And that became the notion of characters, right? So we introduced this notion of characters, right? But for us, it's a little bit different now. For us, the characters form a group, right? The characters themselves form an abelian group called the dual group, right? And you may remember, well, anyway, this here. So now, let me state one fact that we're going to need. One thing was that if you have, I'm just going to state it roughly, if you have a multiplicative function, g going into c, but never vanishing, and if you have a function that is multiplicative, then you have a character. You may remember that we first tried to prove this with the wrong hypothesis, and then effectively Evan pointed out that it was false, and told me that made this. Okay, so so characters, and what are we hoping for? We're hoping that these characters we'll be able to use to reconstruct all the functions on the group. Right? That's Fourier analysis. And you try to express a function as some sort of infinite sum, in this case a finite sum of the characters. Right? Okay. So and excuse me. Okay. So let us call the space of functions that we're dealing with. So G, a finite abelian group, right? And we let V be the complex vector space, right? A vector space over C of functions F, complex value functions on the group, right? And as we saw, this is a finite dimensional vector space, right? In fact, it is a order G dimensional. It's an order G dimensional complex vector space. Okay. And we can put on it an inner product with inner product. So the obvious one, that if you have two functions, you define the inner product to be f against g bar, right? As you sum over all elements in the group, and then you throw this normalization factor. So this thing makes the space into an inner product space, and you can define a norm, of course, by taking the square root of the function against itself. Okay. So we have our group, we have the vector space, right? And we have the dual group of characters. And what we're hoping right, is to be able to reconstruct guys in the inner product space by using the characters, right? The first thing that we're going to need is that G is an orthonormal family. Right? What we're really hoping is that, what are we really hoping? It's a basis, right? We're hoping that G is actually an orthonormal basis of this thing. Well, you know, first thing we're going to go for is that to show that it's an orthonormal family, that the guys are orthonormal. Okay? And I mean, it's not so obvious. At least it's not so obvious to me but I mean, it's not so obvious to me how to get this. But here's how we do it. Okay. So here's the lemma. Let E be a character, be a non-trivial character. Then it turns out that the sum of the outputs is zero. Okay. Why is this sort of something that makes sense? If we think back to our previous Fourier analysis, what does this correspond to?
Like integrating e to the in's or e to the i.
That's right. It's you're taking an integral, and you're saying that the integral should be zero, unless you've got the trivial character. So this is the analog of that. Okay. So something that you want cancellation, right? You want to be able to, you want cancellation. So here's the proof. It uses so E is not trivial. So there exists some element in G where E of E is not 1. Right? And then you consider let's consider the sum that we're trying to show is 0. Let's consider the sum that we're trying to show is 0. We play a funny trick. We say, okay, let's multiply everything by ED. Okay. Right? So, okay, well, since this thing is a character, and this is a finite sum we can pull it in, right? Character, we can combine, right? That's just a property of the character. Okay. Now, this B, if we take the sum over all BAs, well, we get the sum over the whole group again, right? Because multiplying by B creates a one-to-one map on your group, right? You can invert it just by multiplying by B inverse, right? So it's a one-to-one map, and so what we do is we get the same thing as if we just took the sum of the whole group again. Right? Is that okay for everybody? Jennifer, does that make sense? Okay. We've got everybody, if you're summing over everybody in the group, well, then you multiply on the left by B, you've just permuted the guys. All you've done is permuted the group. And then you're summing over the whole group again. So it doesn't change anything. Okay, so what does that tell you? Well, since D of B is not equal to 1, then the sum must be 0. Right? Then we must have a cancellation. So A must be 0. Okay, so cancellation. Cancellation works. You see, e to the 2 mi x or something. Right? But it still works in this setting. Maybe, yes. What is it? How do you know 0 is what? This is, so remember what the characters are. The character is mapping to C. Right? The character is mapping to C. Right? So, right, you're multiplying some number, some complex number, by something that's not 1. Right? E and B. Right? A and B is not 1. This is not 1. This is a complex number. Right? So that says that if this is not 0, then the number is not equal to itself. Okay? Which would be crazy. So we're in the complex numbers. Right? It's not some field.
You don't have to worry about the divisors in this case. You just have to, right?
Say it again. I'm sorry.
You don't have to worry about diagonalizes or anything.
Yes. Right.
Because in this case, it just has to be 0 in whatever space.
I'm not following. Okay, sorry, I'm going to go on. We're in the complex numbers, right? So, what are the 0 divisors in the complex numbers? There are no 0 divisors in the complex numbers. Okay. Okay, so we get this one fact, right? We get this one fact that the integrals are 0, like these guys have cancellation, right? And we're going to use that to show that that the characters are all orthonormal. Right? So proof of the theorem. Proof of the theorem, right? So let's do this in parts, right? Let's say that we have a character, right? And let's consider E dotted against itself. Actually, this part we could have done before. We're not going to use the lemma in this case, right? By definition, this is just 1 over G summation E A bar as A ranges over the whole group, right? And the end. Right? Because you're taking right. E is a map from E is a character, right? So the map from the group into S1, right? So each of these things is 1, right? So you're taking a sum of 1s over the whole group. You get the size of the group divided by the size of the group, which is 1. Right? Each of these EA bar is 1, right? So you get summation 1 over the whole group. In other words, you get the size of the group. It just counts how many guys are in the group. So that's easy. Part 2, right? To show that if E and E prime are both characters, and E is not equal to E prime, right? We want to show that E in the product E prime is 0. Okay, and so do, we say, well, look, consider E prime inverse. Okay. I should have done this backwards, but sorry, I'll do it forwards. Consider this guy. This is a character. Right? So notice that this is a character and it's non-trivial. It's non-trivial, right? Okay. And so now we use the lemma. We say, okay, well, on the lemma, we see that summation E prime A inverse is equal to 0 as A sums over G. Right? But then you notice that E prime inverse is the same thing as E prime conjugate, right? Because this is a map into S1, right? What's the inverse of a point on the circle? By complex multiplication, it's a complex conjugate, right? So in S1, you notice that Z inverse is Z bar, right? So if we're looking at the inverse guy to E prime, that's the same thing as E prime bar. Is that clear? Daniel, is that clear?
Can talk about that,
I'm sorry?
Can talk about that again.
Yeah. Okay, so, right, let me do it backwards, okay? Let me write it backwards. Okay, let's look at this backwards. Let's read it backwards. E prime A bar. Okay, and so the end is that E against E prime is 0. Okay, so let's look at it backwards, because that's actually clear. We're trying to show that E against E prime is 0. Okay. And so we say, okay, in other words, we're trying to show this. Right? These two statements are the same. Okay. Right? Then you say, okay, what's E prime conjugate? Right? This is the complex conjugate, right? So here we are, here is S1 inside the complex plane. Right? And the group is under complex multiplication, right? If this is a point in S1, what is the inverse point? Well, the inverse point is this point, right? Because when you multiply these two guys together, well, you get 1, you get the identity, right? So this is the inverse here, right? Z inverse, which is the same thing as Z bar. Right? Okay. So instead of putting Z bar, instead of putting E prime bar here, let's write this as E prime inverse. Okay. We write this as E prime inverse, and then we notice that this we can think of as E times E inverse. I'm sorry, E times E prime inverse of A. Now, we realize, well, this is just a product of two characters, the character E and the character which is inverse to E prime, right? So, you know, the group of characters is a group. So this guy, and this E times E prime inverse is also a character, right? And by assumption, it's a non-trivial character, right? By assumption, it's a non-trivial character. Okay. And so what we've done here is looked at the integral of this non-trivial character. And we just showed that the integral of non-trivial characters is 0. You see, it is actually clearer going backwards. The trouble with a lot of math is that it's written as if it was created forwards. So you actually have to read the math backwards to understand it. Most of the time, math is written with people hide the tracks of what they did. And then, but if you just turn the paper over and read it, then actually it makes more sense. Okay. Any questions? Any questions? So what we've done, right? We've just shown that that the space of characters, that the collection of characters is an orthonormal family. This tells us, at least from the beginning, that the number of characters is finite, right? Because we know that the dimension of B is the order of G. And we know that the dimension of the span of the characters, right? The dimension of the span of characters is smaller than the dimension of B, right? So you've got these orthonormal guys. You've got these orthonormal guys there. So there can't be more than G of them, right? We know that the size of G prime, must be smaller than the size of G. And what we're hoping for is that the size of G hat, we're hoping that the size of G hat is the size of G. Then it would be an orthonormal basis. Okay. So that is the goal. Right? Goal to show actually G hat has the same size as G, and thus G, the characters form an orthonormal basis of B. Okay. Okay. Okay, everybody ready? Okay, so now things start to get ugly. Okay. Okay, so to get there, to get to this point, to get to the point where to show that this thing is actually an orthonormal basis, we're going to have to go a little bit deeper into linear algebra. Okay, so here we go. So deeper into linear algebra. Place where you maybe never wanted to return, let alone go deeper into. Okay, that's not true. Linear algebra is very cool. Right? Linear algebra. If you go on in math, you take this course, functional analysis. What is functional analysis? It's infinite dimensional linear algebra. Right, so everything in linear algebra, if you teach it in the right way, you're basically setting people up for taking a course in functional analysis. Just like, I guess I said Fourier analysis was infinite dimensional for linear algebra. Different portions of it. So different parts of linear algebra, if you take them into infinite dimensions, it becomes Fourier analysis. Different part becomes functional analysis. So let's recall. Some notions, which I hope you've seen before. I just call it definition. So again, let's have V, a d-dimensional inner product space, and T, a linear transformation. Okay. If for all V and W in V, we have that the inner product TV TW is the same thing as VW. We call T unitary. A unitary transformation. And then there's something that I hope you saw in the algebra called the spectral theorem. So given any unitary transformation T, there exists a basis V1 to VD of eigenvectors of T. So this is basically saying that if you're unitary, then you're diagonalizing. Which is maybe how you saw it in linear algebra. Right? A unitary matrix is diagonalizable. You can find the basis of eigenvectors for it. Okay. So this is the important spectral theorem. So that part I'm going to assume that you've either seen it or just willing to accept it. How many of you have seen it? Some of you have seen it. Well, but you've probably seen diagonalizable statements, right? In linear algebra, right? If you have a real symmetric matrix, then it is diagonalizable. This is basically the complex version of that. So it's actually not, the proof of it is in fact easier than the real case. So what we're going to need is a corollary of this. If V is again a finite dimensional product space, excuse me, and you have now a family of linear transformations on V, from V to V. Okay, we should be unitary, so not without this. If all the Ti are not only unitary, but they also commute, then there exists a basis, again, V1 to VV, of V, of eigenvectors for every Ti. So these guys are simultaneously eigenvectors for all of the members of the family. Okay. That is to say, you can find a basis that diagonalizes all members of the family simultaneously. So we can think of this as not just diagonalizing one matrix, but diagonalizing a family simultaneously as long as they commute with each other. Okay. And of course, the commutation will be the important part. So, and this is the result that we're going to need to get that the dual group is actually an orthonormal basis. Unless we want to take the easy way out and use the structured theorem for finding abelian groups, which we don't, just out of pride. Okay. So here we go. Here we go. This is pretty cool. So it's cool, except that we're going to use induction, right, which is sort of like the most hated method of proof. Nobody will believe you. or people will ask if you can do it some other way, if you do it by induction. Okay, so we're going to do it by induction. So, of course, in the case k equals 1 is the spectral term. Right? You're not commuting with anybody, you're simultaneously diagonalizing. Right? So assume it's true for k minus 1. Excuse me, families of k minus 1. Okay. And so we've got family now, C1 to k. We suppose that there's unitary. Okay. And here's what we do. We do something funny. We say, let's take tk. Okay. And by the spectral theorem, we can decompose V into a direct sum of eigenspaces of tk. So this is the diagonalization statement, right? So each of these things is an eigenspace, right? This is just another rephrasing of the diagonalization statement, right? That you get eigenspaces, and their intersection is at 0, of course, and the total sum of them gives you the whole space back, right? That you have enough eigenvectors to span the whole space. Okay. So in case you're not familiar with this notation, V is W plus Y. It means that basically that you've got these guys are subspaces, and that the intersection is empty, or the 0, right? And then the span of these two things gives you V again. Okay. That everybody in the space can be expressed as an element of here plus an element of here. So maybe that's the right one. Any V in V can be uniquely expressed. Actually, just uniquely expressed as some little w plus little y. So with that in mind, this is just the same statement as you can diagonalize. So by the spectral theorem, you're able to diagonalize. In other words, you can break this guy into a bunch of smaller subspaces. Okay? Everyone all right? Okay, good. Okay. So I'm going to make an observation. Observe. Observe. Given any tj, so take one of the other guys, right? So j is less than k. Take one of the other guys, and you notice that and take somebody in one of these spaces, some v in one of the eigenspaces of tk. You notice that take one of the guys in the eigenspaces, and you notice that, well, look, if we hit the first, but I'm going to write it and figure out what's going on. Sorry. If we look at TK, TJ of V, no, it's right. Sorry. Okay. You look at this thing. Well, you know that these guys commute. You know that these guys commute, right? You know that TKV, well, V is in the eigenspace, right? Is in the eigenspace. So getting with TK, just multiplies it by lambda I, right? And so we get lambda I TJ V, right? Okay, by the commutation. Right? So that says that this vector TJV is an eigenvector of TK, right? TJV is in V sub I. In other words, each TJ preserves each of the V lambda I. These eigenspaces of TK are actually preserved by the other guys. Okay. They're preserved by the other guys. Okay, so we can think of each one as a linear transformation on the subspace. Okay, right? Because it's not the case that when you hit this guy, it goes out into some other space, right? Okay. So each of the TJ maps the VI back into the V lambda I. Okay, so this is really the key, and this is where the commutation comes in. So by induction hypothesis, well, we're gonna do by induction hypothesis, the family T1 to Tk minus 1 is simultaneously diagonalizable, right? Is simultaneously diagonalizable on each V lambda I. On each V lambda I, right? So now we do something. So this does something pretty funny. Like, what does that say? That each V lambda I is in turn decomposable into each V lambda I in turn is decomposable into eigenspaces of the T1 through Tk minus 1. Okay. So each of those guys breaks down further into eigenspaces of these full of the first K minus 1 guys. Okay. So what does that give you? That gives you that V is expressible of all these little bits, right? Where each little bit is an eigenspace of all these guys, but each of those bits lies inside of an eigenspace of the last guy, right? So each of those little bits is an eigenspace of the full family. Okay, and in other words, you can simultaneously diagonalize all of them. Okay. So into eigenspaces of blah, which are also eigenspaces of Tk. Vf. So this is the extension of the spectral theorem, saying that if you have a family that commutes of unitary, if you have a family of unitary operators that commutes, then you can simultaneously diagonalize them all. Thus ends the linear algebra portion of this show. Any questions? Any questions on how we did that? Right. We took the last time and we said, oh look, you can decompose the space into a direct sum of eigenspaces. Then we noticed that because of the commutation, right, and this basically 3 steps, right? Then we noticed that because of the commutation, each of those eigenspaces was preserved by the k minus 1 family. Right? And then we said, okay, well look, because each of those guys is preserved, we can do the spectral theorem on each of those guys. Right? And each of those guys can be decomposed, each of those spaces can be decomposed into eigenspaces, simultaneous eigenspaces of the k minus 1 guys, and they're contained inside the eigenspaces of the last guy. So three steps. Yeah, so I'm sort of hesitant to jump into the last thing, because the last thing is gigantic. The last thing we want to do is to show that G hat, G, A, I, B1, 2, and G hat is an orthonormal basis for V in the space of vector space of functions, actually. So maybe, well, I'll just get started on it. Okay. So here's the idea. No, I'm going to do it. So, yeah. So I'm sorry. I'll start it next time because it's really a long. It's really long. So just to comment on the homework. So I guess I misunderstood where people were. So ignore the last 2 mails that I sent out saying that there's describing a homework for this Friday. I guess you all have already have a homework that's due this Friday, right? You already have a homework that's due this Friday. I sent out something saying, here's a homework that's due this Friday. That would give you 2 for this Friday. Unless you want to do 2 for this Friday.
We could add 2 problems, maybe we could split it, like add 2 of this one to this one to the next, we have to do it all.
So, maybe. So I sent out a mail giving a homework for this Friday and a homework for the next Friday. Both of those homeworks are actually pretty small. Okay. So I think the thing to do would be, so maybe Jennifer's suggestion is good. Let me look at the first mail and say, add this 1 or 2 problems from the first mail to this week's Friday, and then the other problems will go on the next week's Friday. Okay, so we'll sort of split it. Because the homeworks, these 2 homeworks that I just sent out are not that big. Sorry about this. If people want another day or 2 to work on it, that's fine with me. Also, like I said in the mail, the graders have been saying that some people have been using the solution sets online. Apparently, there's solution sets online. I tried to get rid of them by sending mail to the person who had them, but maybe they've come back online. Try not to use the solutions online. And basically, just don't do it because then it doesn't really help you that much as a, it's like you don't grow that much if you use a solution that's online. So it's much better to just try it, and even if you don't get the answer, you just write down something. That's better for you as a mathematician. That's better for your growth as a mathematician than to just look at somebody else's work and then do it. Certainly I've worked with other people, and I've done this before. Like I work with other people, and I say, oh, I didn't understand this at all. I'm just copying this person's work, and of course I learned nothing. Right? So don't do that. And then the last thing I wanted to say was, at the beginning of the term, I asked people to each week try to put a question on the forums. Nobody has been doing this. Try and do it. Okay, so the goal is to ask a question. Ask a question that's not answered in the book. That is, you should be able to formulate some questions at this point, right? And you should be able to ask some question that actually goes a little bit beyond what the book has given you, right? Try to ask. So if you don't mind, I really do want people to ask these questions. Even if you didn't, so they're like, I think we're on like week 13 or something like that. Well, just go back and make up some questions, and yeah. But if you didn't make up a question, please go back and try and make up a question. I know it seems sort of silly, but actually this is key. This is really crucial in becoming a mathematician. This is crucial. Right? If you cannot make up good questions, then what can you do? Nothing. Right? What can you do? Maybe you can somebody will ask you a good question. You have to wait for somebody else to ask you a good question, and then you figure it out. Right? But you have to be able to make up good questions. So make up some questions, and I'll go through and say, this is a bad question, or this is a great question. Right? It's practice for me as well to try and explain why a question is good and why a question is bad. Okay, so although this is not, this factors into your grade in some small amount, but I actually think that this is a really crucial part of the course. Okay, so please go back if you haven't, and try to go for each week some question relevant to the material of that week. Okay, please. Thank you. Okay, that's it.